first of all defining what you mean by a linear combination of vectors. Now, just before that, our capital V here will represent vector space, and K will represent the scalars. In this lesson, our K will just be the real numbers. Our K will be the real numbers. So when do we say that vector V is a linear combination of the other vectors X, Y, and Z? So that is a question we seek to answer in today's lesson. So for us to say that vector V is a linear combination of the vectors X, Y, and Z, what we mean is that we can find scalars, real numbers, these are the scalars ABC, such that V can be expressed in this form. So if V can be written as AX plus BY plus CZ, then we say that V is a linear combination of vectors X, Y, and Z. So if these scalars exist, the scalars A, B, C, if they exist, then V is a linear combination of these vectors. But if they do not exist, then V is not a linear combination of these vectors. So let's look at an example. So the first example that I want to look at is, want to see if vector V can be written as a linear combination of vectors U1, U2, and U3. So I want to see if this vector V here, which equals to 1, 11, 21, can be written as a linear combination of U1, U2, and U3. So in other words, what we want to see is whether we can find scalars A, B, C, whether these scalars exist, such that V can be written as A U1 plus B U2 plus C U3. Now, if these scalars A, B, C exist, then we say yes, vector V is a linear combination of these three vectors. But if they do not exist, then we say it's not a linear combination of these three vectors. So how we do it, we begin by letting ABC be our scalars. So from the definition of linear combination, we want to see whether A times U1 plus B times U2 plus C times U3 gives us V. So this one these are matrices. We now have to multiply scalars by matrices. So this will be 3A plus 2B minus C equals to 1. That's what I have here. Then this will be A plus 4B minus 3C equals to 11. That's what I have here. And then this will be negative 2A plus 3B plus 5C equals to 21. That's what I have. So we have this system of linear equations. And in our previous video, we learned how to solve systems of linear equations. So we will solve this by row reduction and see whether we can find the value of A, the value of B, the value of C. So what I did was, since this I can write this in matrix form, but I decided just to work with them the way they are in equations. But I know that if I were to write in a matrix form, this will form the first row, the second row, the third row, and this will form the first column, the second column, the third column, and the fourth column. if I were to put them in matrices. So I'll treat them as such. I'll treat them knowing this will be first row, second row, third row. And this will be first column, second column, third column, and fourth column. So that when you hear me talking of a column and row, then you will know what I'm referring to. So looking at this element here, this is non-zero element. Using our knowledge of how to solve a system of linear equations by row reduction, I want to create a zero in this position, another zero in this position, using this first element. In fact, it would be easier if we were to divide the whole of this row by 3, but I just want to leave it the way it is. So that I want a 0 in this position. So for me to get a 0 in this position, what I'll be doing will be row 2 minus a third of row 1 to give me my new row 2. So let's just see how I obtain this using this. Row 2, I have A. So A minus a third of 3A, that one gives me 0. That is why you can say I have a 0A here. Then I would have 4B minus a third of 2B. A third of 2B. So this, of course, the LCM would be 3. So this would be 12B minus 2B. That will give me 10B over 3. That's what you see here. Similarly, for this one, I would have negative 3C minus a third of negative C. So this is the same as negative 3C plus a third of C. And of course, the LCM again will be 3, and I would have negative 9C plus C, which will give me negative 8C over 3, and this is what you see here. Doing the same thing for this, I would have 11 minus a third of 1, and this again will give me that 3 minus 1, which is that 2 over 3. Now, I achieved getting a 0 in this position, so the other thing I want is a 0 in this position. So to get a 0 in this position, I will take row 3 plus 2 over 3 of row 1. So if I take row 3 plus 2/3 of row 1, let me see what I have as my third row, the new third row. So what I would then have in this position, I would have 2A plus 2 over 3 of row 1, which is 3A in this position. So this is just 2A. So minus 2A plus 2A will give me 0. So you can see I have 0A here. And then, what about, let me just erase this. What about in this position? I have 3B plus 2 over 3 of row 1, 2B, of 2B. Of course, the LCM will be 3, and this will be 9B plus 4B, which gives us 13B over 3. 13B over 3 is what you see. And then in this position, I have 5C, just write it clearly. 5C plus 2 over 3 of the element in row 1, which is negative c. So the LCM is 3, and this will be 15c, 15c minus 2c. 15c minus 2c will be 13c over 3. That is what I have there. Then finally, 21 plus 2/3 of 1 plus 2/3 of 1, and I would have 65 over 3. So I've achieved what I wanted. What I wanted was to have a 0 in this position and another 0 in this position. Now, my row 1 remains the way it is throughout, because I already said that I do not want to divide by 3 to have 1 here. Just want to leave the way it is. So you can see what I now have. What I now want to use this element to clear the second column, but I only consider the elements below it. So I want the elements below it to be 0. So I want this element to be 0. This position. The element in this position will be 0. So as you can see, this is 10b over 3, and this is 13b over 3. So how do I achieve a 0 in this position? So for me to get a 0 in that position, I want row 3 minus 13 over 10 of row 2. 13 over 10 of row 2. Let me see, what is 13 over 10 of this? So 13 over 10 of 10 over 3 will give me what I want. I want 13 over 3 to subtract from this, where I have a 0. So this is what we shall be doing. So what we shall be doing is, I'm taking row 3, and then from it, I subtract 13 over 10 of row 2. So let's see what we have in the next column here. The first row remains where it is. The second row remains where it is. It's the third row that I want a 0 in this position. So I take row 3, that is 13b over 3 minus 13 over 10 of row 2, which is 10 over 3b. So this gives me 0 in this position. So you can see a 0 there. Then the next thing, I want to work out this. So I have 13 over 3c, and then minus 13 over 10 of negative 8 over 3c. Okay, so what does this give me? Let me just leave it. Just leave it. Let me not even simplify. Let it just be that way. Or I can even simplify. I can simplify 2 goes here 4. No, 5. And here 4. So that I have 13 over 3c. This minus terms, that minus will be positive. And this will be 52. 52 over 15. C. Yeah, I took this one. 13 over 3c minus 13 over 10 multiplied by this. So I've just simplified. And the 2 was to go here, the 2 goes there. So that would be 52 over 15. So the LCM is 15. The LCM is 15. And so the other one, I just left it to be 30. So you can see the one I have here is 30. I just left it. I have not simplified this. Not simplified. So, but you can simplify it. You can simplify. So if this is 13, 15, this will go here 5 times. 5 times that, 5 times 13, I would have 65 plus 52. So that gives me 117 over 15. 117 over 15. Because even this one, if we had to cancel it, we would still get 117 over 15. We still get that. Now, so I have that. I do it also for this, and if it's 117 over 15, this will also be 117 over 15. So what does that mean? After I've reduced my matrix, my equations to this level, my system of equations, I've reduced them to this level. I begin solving from the bottom, just the way we discussed in our first video on solving systems of linear equations. Now, from this last equation here, it's true that C is 1. So solving this, C would be 1. So we solve from the bottom going up. So C is 1. Placing here 1, we can get B. So I did and found that 10 over 3B will be the same as that 2 over 3 plus 8 over 3. So the right side is 40 over 3. 40 over 3. And the left side is 10B over 3. So multiplied by this reciprocal on both sides, the reciprocal of this, B would be 4. B would be 4. We now proceed this first equation, substituting the value of B and C to get A, and A is 2. Now, since our scalars exist, it means that the vector U, the vector V, can be written as a linear combination of U1, U2, U3. And when we do that, we find that V is equals to 2U1 plus 4U2 plus 1U3. So we've written V as a linear combination of the other vectors. But what was our question? Let's go back and see what our question was. Our question was, is the vector this a linear combination of U1, U2, and U3? And we already said that if the scalars exist, if the scalars A, B, C exist, then V is a linear combination. And in this example, we've seen that the vectors ABC, no, the scalars ABC exist, and therefore we conclude that V is a linear combination of U1, U2, and U3. So that's what I wrote here. I said thus, vector V can be written as a linear combination of these other 3 vectors. And it's here. Let me just clear this. Now let's take another example where we understand the knowledge of linear combination. There's another example here. Remember that in our first one, the only difference is that the first example, the vectors were given to us in column form, and this one, the vectors are given to us in row form. But the way we approach it is just the same. The question is, write this vector as a linear combination of these other 3 vectors. So by definition, we're supposed to find scalars x, y, z such that this vector v can be written in terms of these others, this way, that v equals to ax plus by plus cz, and so on, that way. So I arranged it x times a plus y times b plus z times c is equals to v, and then just simplified. These are matrices, so we just multiplying by scalars. So multiplying this by scalars. So let's see. And we are doing it the same thing, just doing the same way. So this would be 2x minus 3y plus z equals to 2. And this would be 3x minus 4y plus 3z is equals to 7. And this would be 2x plus 3y plus 2z is equals to 8. From there, we want to solve this system of linear equations. Yes, the same way we solved it in the first example. I use this 2x to create a 0 in this position and another 0 in this position. So we want to see how we create a 0 in this position. For me to create a 0 in this position, I'll want row 2 minus 3 over 2 row 1. That will give me a 0 in this position. And for me to get a 0 in this position, that one is easier. I just need row 3 minus row 1. So let's move with these two together. Let's move with them together. So the first row remains where it is. I want a 0 in this position. I take negative 4 y minus 3 over 2 of row 1, which is negative 3y. Negative 3y. And this gives me the LCM as 2, and this would be negative 8y minus, it becomes plus because minus 6y. So you can see this would be negative 2y over 2, which would be negative y. Negative y over 2. Just a minute. No, this is 9. This is 9. This one here is 9. Let me just erase. This one will be 9. So it will be plus 9y. So if I do this, this would be negative 8 plus 9 would be y over 2. That's what I have. What about in this other one? Subtracting this from this, I have a 0 there. And then 3y minus 3y, that gives me 6y. 6y, and that's what I have here. Now let's come to this other element. In fact, in the third row is very easy. I'll just take 2z minus z to get a z. But what about here? Here we say that we would have row 2 minus 3 over 2 row 1. Row 2, I have 3z minus 3 over 2 row 1. Row 1 is z. So this is just 2, and this would be 6 minus 3, which would be 3z. So 3z over 2. Similarly, I did for this, and I found 4 and 6 respectively. Now, so from there, I want to use this element to have a 0 in this position. So again, how do I achieve that? By multiplying this row by 12. So I multiply this row by 12 and then subtract from this row. So I have row 3 minus 12 row 2. So what do I get? This one times 12 would be 6y. From this I have 0. This one times 12, I would have 18z. From this I get negative 17z. And this one times 12, I would have 48. From this I have negative 42. So I have this. So at this point I will say that we solve from the bottom going up. So solving from the bottom going up, the last equation there, you can get the value of z by dividing both sides by negative 17. And I did that. I found that z would be 42 over 17. 42 over 17. We then move to the second last equation. Substitute the value of z here and find y. And I did that and I found that y was 10 over 17, and then x was 11 over 17, respectively, when you move to the first equation. Now, what is important here was what was the question? The question was, write this vector. It's not like the first question. The first question was, we were supposed to tell whether, the first example here, we were supposed to tell whether this vector v is a linear combination of this vector. So we're just supposed to find if the scalars exist. And if the scalars exist, we say yes, it is a linear combination. But for this particular one, we've been asked to write it as a linear combination. We've been asked to write this as a linear combination of this. So that means after finding the scalars, substitute them here. And that is what I did. That's what I did. I found that v was equal to 11 over 17a plus 10 over 17b plus 42 over 17c. We've written it as a linear combination. So v is a linear combination of these other vectors. Now, so just doing as I said, we do various examples to make our work easier. So I want to look at another example here and see how to approach it. And the question is write this D as a linear combination of these vectors. So in other words, can you find scalars x, y, z such that D or xa plus yb plus zc is D? Can we find that? And if those scalars exist, then we can write D as a linear combination of these other vectors. So that means, so this x times a, let's just do it. This is 1, 0, 1. 2, 2, negative 1. Negative 1, negative 2, 2. 3, 1, 3. And then just expand this. Expanding this would be x plus 2y. X plus 2y minus z equals to 3. And this other one, x would be 0. X times 0 is 0. So it will be 2y minus 2z is equals to 1. And this other one will be x minus y plus 2z is equals to 3. So we have this system of linear equations which we solve the same way we've been doing above. So let me see what I got when I solved it. So I solved the same thing. I did it. And this is what I was getting. This is what I was getting. So this is my final the final column of this. So I just reduced the same way I've done the first and the second exam. But now I'm interested with this last bit, this last row. What this last row means is that x, 0x plus 0y plus 0z equals 7.5. This is what this row means, and this is not possible. We cannot find scalars x, y, and z such that when you multiply them by zeros and add the results, you get 7.5. That's a contradiction. That is not possible. And so once our last row appears like this, or any of the rows once it appears like this, that the sum on the left side is 0 and the sum on the right side is an 0, then it means that this system has no solutions. In other words, this scalar x, y, and z cannot be obtained so that when you multiply them by 0, you get that. So it's not possible. The system has no solutions. So the last row of the last part implies this, which is impossible, and therefore the system has no solution. Remember in our last video, we said that a system that has no solution is called inconsistent system. Inconsistent systems. Inconsistent. So this system here is inconsistent. It has no solution, and therefore D cannot be written as a linear combination of the other vectors. It cannot be written as a linear combination of those other three vectors. So we've seen an example where we cannot write a vector as a linear combination of the other vectors. And we've seen two examples where it's possible. So this knowledge can be extended even to polynomials. If we have polynomials, we can extend the same knowledge to polynomials. And so let's see how we do that. So the question is, we have this polynomial and these other three polynomials, P2, P3, and P4. So the question is P4 a linear combination of P1, P2, and P3? If it is, then write it as a linear combination of this P1, P2, and P3. So just as we've already discussed, for us to write P4 as a linear combination of the other vectors, we need to see if we can find scalars x, y, z such that x times P1 plus y times P2 times plus z times P3 gives us P4. Let's see, x times P1 plus y times P2 plus z times P3 is equal to P4. We just expand. This will be t squared x, 2tx, 3x, and this one will be 2yt squared, 3yt, and 7y. And this will be 3zt squared, 5zt, and 6z. And this will be 3t squared plus 7t minus 4. So at this point, we would collect the like terms. Those that have t squared, bring them together and factor t squared out. So what I mean, I have this, I have t squared, I have this. So what I will be doing, since t squared is common, I would put it outside, and inside I would have x, and then this other one is 2y, and this other one is 3z, close the bracket, equals, on our right side I have 3t squared. So t square and t square cancels. So I'm left with x plus 2y plus z, 3z is equals to 3. And that's what we see here. X plus 2y plus 3z is equals to 3. Now, so I also do for those that have t. Those that have t, I also equate them. Add them on the left and equate them to the one on the right. So the ones that have t, let me factor t out. I have this one, which is 2x plus 3y plus 5z is equals to 7t. So t would cancel out, and I'm left with 2x plus 3y plus 5z is equals to 7. So that is this equation. Then finally, I equate the constants, those without t. So I have 3x plus 7y plus 6z is equals to -4. So those are the constants. So that's what I have. So this, doing what we've just done, gives us this system of linear equations. This system, we have 3 equations here. And we solve the same way we solved the first 3 examples. We reduce this, reduce that, and my final equation will be this. This is my final column, after reducing the same way we've done the first 3 examples. You can see this system has solutions because we can get the value of z. It has solutions. It's not like the previous one where this part was 0 and this other part was non-zero. So this one has solutions, meaning that our polynomial P4 can be written as a linear combination of the other polynomials. So the question wanted us to write P4 as a linear combination of these other polynomials. So we just find z to be 3 here. You can see z is 3 using this last row. Proceed this other row and find y as -4. Then proceed this other row, substitute y and z and find x as 2. So since x is 2, y is -4, and z is 3, P4 can be written in terms of P1, P2, and P3 as this. This is what the question wanted us to write. So it's very easy writing a polynomial as a linear combination of the other polynomials. Even matrices can be written as a linear combination of other matrices. So the knowledge of a linear combination is very easy. So you just go through the examples that we've already gone through, and you will see how easy it is.